Hello and welcome to one more day of the Advent of Code. Today, day 12. I have read the statement a couple of hours ago, haven't got to code yet. So let's see. First, we can copy this input, 12.in. Let's see. 12.py. Let's read this input. So, well, we already see what this looks like. This is like some kind of the height of each point is the letter. You want to go from the start. I don't find the start here. It's a capital S. Oh, here's the start. And we want to go to the end here. All right. So what we need to do is we can read this grid, for example, as open 12.in.read.splitlines. Let's print this grid. We got all this. Sometimes it's better to, well, we don't need to modify this grid for now, so we can keep it as a list of strings. What do we want to do? Well, we want to find the I and J of the start. So we could have start is the -1, -1. End is -1, -1. So we could do now for I. Well, let's print the length of the grid and the length of grid 0. I think this is a square. Oh no, it's not square. Really? It looked like it was a square. Okay, so never mind. We could say n equals length of the grid and m equals the length of grid 0. That can be helpful. So for I in range n, for j in range m, if grid ij equals s, then s equals ij, and we want to do the same for the end, right? Let's print se. Okay, we got these two positions. So what we want to do is we want to go from s to e, moving in different directions. These directions are either 1, 0, -1, 0, 0, 1, 0, -1. These are the four directions we can go in. We start from S, and then what we want to do is what is called a BFS, right? A breadth first search. We want to go one step in all possible directions until we find E, because what we want to find is the fewest steps required to move from one position to the other. Let's count these steps equals 0. And then usually what I would have for doing a BFS is this kind of structure. And in Q1, we are going to add the starting position. So what we're going to do is, while length of Q1, while there is something in Q1, we're going to visit. So for position, or for ij maybe in Q1, because these are going to be pairs of positions, now we want to move around here. And here we could also have sin, which is a set, and we don't want to visit points twice, right? So the first thing we're going to do is we're going to mark this, or not as sin. What we're going to do is we're going to get the neighbors of all this. So we could have here a handy function. So what are the neighbors of ij? So for increment a, increment j in direction, new I equals I plus increment I, new j equals j plus increment j. Something is wrong. This is not being formatted correctly. So if 0 less of equals new I less than n and 0 less equals nj less than m, then we're going to yield the new I, new j. So here what we're going to do is for new I, new j in neighbors ij, if ny, nj not in scene, if we haven't seen this one, what we're going to do is we're going to push, to append this new neighbor. And we're going to mark it as seen. So same as we have this, seen, add. So for each neighbor, if it's not seen, we do this. Finally, we could add here if ij equals if ij equals the end, we break. And we are going to increment the steps plus equals 1. Let's print the steps and run this. Okay, we are hitting an infinite loop. So let's see. Okay, and finally what we need to do is we're going to pop this element. So q1, well, not q1. What we're going to do is q1, q2 equals, so we're going to move q2 to q1 and we're going to empty q2. 97. Should we print this or should we wait a little bit? I'm worried of off by 1 errors. So let me edit 12.example and paste this. Let's run this with the example first. 13. Okay, 13 is wrong. So this is not right. The number of steps is 13. 1, 2, 3, 4, 5, 6, 7. Oh, wait. I'm doing something wrong. I'm just moving directly, but there's a condition. You can move if the elevation is at most 1 higher. So you can only move if it is not seen. Let's just unsay. If the order, so the character of grid and I and j, if this order minus, so the character, the order is the ASCII character. If this number is less than or equals to 1, so the new one is at most it can be 1 higher, right? At most it is 1 higher. Is this right? Grid of ny and j. I think this is right. Let's print ij 0, 0 and nothing else. So this is not right. So let's print this difference. 14. Oh, because then for the s, this is a special case. Let's say if ij equals s or 26. Still not right. 26. So we found this is the fewest possible. What this says is that this is indeed the fewest possible. And we have found some way to get in 26, which is apparently should be impossible. I think there's no need to submit the solution because this is clearly wrong. Maybe. What are the steps? During each step, you can move exactly one square up and down to avoid needing to get out of this climbing gear. The elevation of the destination square can be at most one higher than the elevation of your current square. That is, if your elevation is m, you can go to n. This also means that the elevation of the destination square must be lower than the elevation of your current square. Okay. For example, destination square. Maybe can be at most one higher. So can be one higher. You always need to climb up. Is that true? Maybe you can, or in 0, 1, do you always need to 31? Yeah, it seems that you always need to go either on a horizontal line or up one. Let's see if that is right. No. Too low. Does it mean that we always need to go? Oh, sorry. I didn't mean to do this. Okay, that is the same. Does this need to be 1? No. Let's go to the example. 26. Why did this work? This worked, but it's not right. Because if ij is e, then we need to break. Okay, let's understand the example. S and the E. Your current position has elevation. Oh, this has elevation A. Oh, A and Z. Okay, so that I forgot. So then that means that grid S0 E0 equals A. Sorry. S and E and 1 and 1. And this one is Z. So that's different. So this I can remove. Okay, we cannot have this assignment, so here we can do a list of S for S in, we convert the strings to list. Okay, 32 minus equal 1, 32. Okay, so maybe we just want to do steps minus 1. Let's see if that is right. 401. Submit. Too high. Okay. Too high. So maybe steps minus 1 is not what we want to do. Here, let's see, most higher than the elevation of your current square. That is, if your current elevation is m, you could go to n, but not to o. This also means that the elevation of the destination square can be much lower than the elevation of your current square. Okay, so it can be, the destination can be much lower than the elevation of your current square. So this is minus equal 1. So for each neighbor, if not seen, and if it's possible to move, then we append, we add this to the ones that we have seen. Initially, we are here. So for each step, maybe we want to do it like this. If ij equals e, then we break. Let's say, because we have been able to visit it, right? It says 32. which I don't think is right. So is there something else we're missing? Here you start in the top left corner, blah blah blah. You can spiral down in the above diagram the symbols. What is the fewest steps required to move from your current position to the location that should get the best signal? Is still E. Start and the location that should get the best signal. Your current position S has elevation A, and the location that you should get to the best signal has elevation Z. A, Z. Neighbors, blah, blah, blah. If this is the end, we break. For NJ in. If not in scene, we append this, we add this to the ones we have seen, we change the step. Steps IJ. So 0, 4, 7. Why 4, 7? In the example, we start from the 0, 0, right? Yeah, so something is wrong here. Oh, wait. Here we are. 0, 0. From one step, we go to either this one and this one. Another step, we go to 1, 2, 3, 4, which is 1, 2, 3. So in one step, let's print steps Q1. So here, step 1, we are in the origin. In one step, we go to A and A. And in two steps, we go to B, B, and A, right? Why do we have 4? Oh, we're going back to 0. But we should not be going back to 0. We should not be going back to 0. So we're making it seen when we add it, but we should probably also mark it. Well, we could also mark it as seen here. Seen.add ij. 32, but that makes more sense. Okay. And the end is the 0, 1, 2, 0, 1, 2, 3, 4, 5. So in 31 steps, if E in Q1, break. Okay, it's another way of doing the same. Let's see what happens. We had that 401 was too much. 394 is just right. Okay, something was wrong there. Let's see the second part. Any square at elevation A to the square. Sorry. So you'll need to find the shortest path from any square at elevation A to the square E. Okay, that seems very easy. So instead of doing this, we're going to do this. For I in range N, for J in range M, if grid ij equals A, Q1 dot append ij. 388. Okay, that's right. So let me go grab a coffee and let's do this refactoring in a minute. Okay, I'm back. Let's just see what we did and how we can improve our solution. So what we had to do in this problem is a breadth first search, what is called a breadth first search, because we move one step at a time and then we find until we find the solution. The first part, we started from the S, and in the second part, we started from all positions which had an A. We can improve this solution a lot, I think. So, and we will do it in the following way. Okay. Where could we start? Well, we had some problem with the off by one errors that I commented the other day. We can remove this print. Well, the first thing we should do is we should have a function for running this def bfs, and instead of break, let's return steps. Print bfs. Let's send this. Well, this is the initial for part 1, and this is, we can do a list comprehension here. So this is ij for I in range n, for j in range m, if grid ij equals a. Okay, so I think we can get rid of this. This is q1 and q2 is an empty list. Okay, this is right. So p1 equals this, and p2 equals this. We assert p1 equals 394. So, and we assert this is 388, which is what we submitted. 394, 388, and 394. So this is part 1 and part 2. Okay. Part 2. Okay. So now we have this BFS function. We had these neighbors. These neighbors, I think this is something that we can, I don't know, we can see. In the other day, we used the trick of using complex numbers. We might want to use complex numbers. Maybe yes, maybe not. We'll see. So how can we simplify this even more? So if E1, if E in Q2 in Q1, so if this is the end, I guess we could also do the same, right? If E equals ij, return steps. That's what we were doing before. That is right. Okay, that is the same. I think it's a bit more clear what we're doing. Steps plus equal 1. Seen. And then for each neighbor, if we can visit the neighbor and it is not seen, then we append and we add. Pretty sure we can simplify this code a little bit. Then we have this grid neighbor. So we're using the grid as is. We could also have used dictionaries instead of this grid, and we might want, if we use dictionaries, we might simplify the code a little bit, but I'm not sure yet if that is what we want. I'm not 100% sure if that is what we want. So instead of using these directions, we could use what we did the other day. So 1 minus 1, 1j minus 1j. So that would simplify the things. We would use complex numbers instead of these pairs. And that might make it easier. But I'm not sure. I'm not sure. So what I want to do now is simplify this code. Well, it's important to see. I mean, this BFS function, I don't like it either. We should have, I mean, this could be initial positions, let's say. So we could do Q1, Q2 equals initial positions. This would be more understandable as a parameter. Then we have these steps 0. And what we do, of course, this is the same as an AND. And then another thing we have here, which I don't like, is that we could say, you know, n as a neighbor. So we could say n0, n1. And here we could say n. We could change this for n. And we could change this for n. We could call it n. We could call it position. And the same for ij, right? So this is the, I don't know, the position. We could change it for position. We could change it for position. And here this is position 0. Sorry. And this is position 1, right? Okay, what did I do wrong? Position 0, position 1. Well, this is the name, again, of position. So it has pros and cons, right? Another thing we could do is we could pre-calculate what are the neighbors of each position, right? So we could create a graph. We could create a graph initially. So the graph would be, it could even be a dictionary, right? So ij, have a list of the neighbors of ij for I in range n, for j in range m. So this graph, let's print it. It has all of the neighbors, like up, down, and so on. But we could also add this condition, right? And so they are neighbors, so you can visit from ij, you can go to this ni and j, which we might also want to write in a single line. If also this holds, right? That's equal to 1. And here this is the grid of n I and j I j. So this condition, which means that this ni and nj are inside the grid and this, that makes the graph be a little bit smaller. So we can see that, for example, this one here in the middle, we should see that it doesn't have 4 neighbors. So is this true or is this not true? I don't really. If this and grid ni and j minus grid ij Okay. Yeah, for example, this one only has one neighbor, which means that we can only visit one position. Another way of doing this. So the problem with ni and nj is that we need to compute this. But another way of doing this would be return, and it would be I plus AI. A is like the increment, it's like a capital delta. That's what I'm trying to say. So we return this for this in directions if this holds. The problem with this condition is that now we don't have the ni, so this is I plus AI, j plus aj, plus AI. How is this? How is this formatted? Is this right or not? Okay, 4, 4 of the force. Okay, so this is formatted in this way. So this is another way of generating these neighbors. It seems to be longer than what we had in the past before. So maybe there's no need to do this list comprehension. Just do it this way. The point is that now next we could also call this neighbors. Seems unnecessary. So now we have this graph. So what this graph help us is that here we can do this simpler. We can do for ni nj in neighbors of this. Oh wait, not neighbors, sorry, in g I or this ij, and now we don't need to do. We only need to check if this is not seen. If n, or this is just the neighbor, if n not in seen. Okay, there's something wrong here. So this is not ij, this is the position. Okay, now this works. So this graph can help us simplify this Another thing we could do is we are doing this if n not in seen. If this is not seen, a different thing we could do is maybe, what if we did this? Would this work? Assertion error. I want to remove the ones which are seen. So here we're just pre-computing the graph using this function here. This direction, we use it here. We could have this in line. What else could we do? So I think we don't need to initialize this. These are just initialized here. We set these two values. So this grid A, Z, we use NM for which is just helpful. So what else could we do? Well, we could maybe simplify this a little bit even more. So what are we doing here? For each position in Q1, if this is the end, we could also do this, and here we return steps. I think it's better to have this. Check in here, and we return -1 if there's a problem. So this is, if this is the end position, we return the number of steps. Otherwise, we have seen this position, and for each neighbor, we append it to the scene. What else could we do? So for I, J in range M, if this is an S, if this is an E, set these values. So where are we using this grid? In the grid, if we wanted to convert this grid to a dictionary, I think the solution would be slower, but it might be faster, you know? So here we would do ij equals character for I line in enumerate this, for j c in enumerate line.strip. Say, call it this grid 2, and this grid 2, I think this is an enumerate and this is an enumerate, which we need to close. So let's print this grid 2. Yeah, that's all to have. So its position has a character, right? So now let's keep this in a parallel reality in which we did this. We're not going to print it, but now we would have in fact, we could do this for instead of doing this, we could have for I row in grid, for j say in row, oh wait, in enumerate grid, in enumerate row. So this grid 2, we have read this other one, print the grid 2. Okay, so now what is S? So S is, if we do a dictionary of zip grid 2, if we print this is a Python trick that we can use to reverse this. And if we print the S, let's see, what is the thing? Sorry, what did we see here? Okay, this is a dictionary. No, this is not right. Oh, dot items. Is this right? No. what do I want to do? What I want to do is I want I think I'm not doing this right. I want to do vk for kv in this. I want to transpose this. So the transposition is each character has a position. So this, which we want to do is s equals s. If we print s, it is 20, which is correct, I think. And if we print, and then the same for e. SE 2052, and if we print here SE, it's the same. Okay, so this is right. So this is a way of doing this. And here in grid 2, we can do just S equals A, E equals Z. So here we could even do grid 2 E equals Z. So this is in the, in a separate, even here, instead of this enumerate, we could say this grid ij for I in range n for G in range M. And that would work too. So this is, we're going in this parallel universe where we use this grid to simplify things. Let's move this down and go to the neighbors. How do we re-implement this neighbors function in this new world? So this is neighbors 2. And what we have here is, well, maybe this is the same. Let's keep it as is. Now what we would do is for ij in grid2.keys, print g. Well, if this works, for post in this, or for ij in this, s is not defined. Okay, because we have to put this down here. Okay, so one good thing, I think I'm going to go with this alternative solution of this grid 2. Let me see where we're using the grid. Okay, now we're only using the graph, right? So we can forget about this. So we can rename this grid here. So just use the new name, forget about this. And here in this grid, we just need to use the Ni and J, Ij. So we have this. Let me make this a little bit longer. Okay, so we have this Ij and the grid 2. So this should be working. Where are we using grid 2? Here. Key error. Okay, where are we using the grid again? Grid. Okay, grid. So grid ij again. This is ij. So here, instead of doing this, we could say k for key v in grid.items if v equals a. I think this is working. So now we can simplify. We can simplify this a lot. Using a grid will help us in another thing, which is this. We don't need to do this check anymore, because what we need to check is if ni and j is in grid and these orders have this condition, then we already know we are inside the bounds, because we are not checking the bounds, but we're checking the values in this list. So what we have here, so here again, this is the key, this is the key, and this is the key, and this is the key in the grid. So this is also works. And now this, we can check the neighbors of this position by checking. So this is the position. And now here we could say position 0, position 1. Okay, neighbors takes 2 arguments, well, because we factored it now. But where I want to get, I think here we also did, this is unnecessary. Okay, so where I want to get to, I think also this n we don't need almost anymore, and this m we don't need anymore, because we're using this grid, we are refactoring this. So instead of grid, we could have here lines, and instead of lines, what we could do is IC character. I think this is what I had before. For I in enumerate lines, for j for IL, and for j C in enumerate L. So that does not work, but we don't need this anymore, right? Okay, so now here we could maybe here open 12.in. Would this work or not? Yeah, it works. So now for each line, we're reading the grid here. So we read the grid and save as a dictionary. That is great. So we were able to read this in a single line. Then we can do this, finding this S and E here, we could also, well, we could simplify this, but and now I think we can generate this graph also in one line. Well, one thing we could do is using the complex numbers instead of these pairs. So what we would do here is I plus j times 1j. So this, of course, this is not going to work. But what we can do now is this increment, we could call this increment in 1 minus 1, 1j minus 1j. So the next is pos plus inc. We replace this by n, replace this by n, position, yield, n. And now this is already working. So if you see this is position plus inc. We could also, instead of calling this, we'd call this d, which would be in direction, and this would be position plus D, position plus D, position plus D. So what we have now suddenly is a very simple. Of course, this could be a list comprehension, right? So we could have this as a list comprehension, and we could have this here. Instead of K, we can say this is pos, because this is what it is. This is the position. And instead of having this list of what we want to do, this is, so what are the neighbors? The neighbors for this position are this. They are position plus D for D in all these directions if this condition holds. That's all we need. And this is already working. So now we have these list comprehensions. So for each position, we have position plus D for these directions if this. So now we have our graph correctly formatted. So here we create graph. We have the initial positions. This E, okay, start, end. For KV, VK, we're doing the, like, transposing this graph. So here we have this graph, and now let's simplify this BFS a little bit more. So here we would say also end. I think it's useful to set the parameter that we want to send here. I would say if position, sorry, so it would be if position equals end. So instead of having these global variables, we have these initial positions. Maybe, well, initial positions, that's fine. So we would have these steps, scene. This scene and steps could be a dictionary, okay? And for each position, we save the numbers of steps. So instead of saying scene, what we would do, or what we need to sum, right? Well, we would have steps equals the steps of. So what we would do here, now I'm trying to do two changes at the same time. So if this is not seen, if n not in scene, it would be not in steps. What we would have is steps of n equals steps of position plus 1. So here, no, this would work. Doesn't work. So steps is this. Well, we have a problem with, steps would be 0 for, so it would be pos 0 for pos in initial positions. Okay, it worked. So here the steps are 0 for each position in these initial positions. And then we have these queues. So while the length of Q1 is larger than 0, for each position in Q1, if this is the end, we return the steps of this position. And for each neighbor, we could also call these neighbors, neighbors. Sorry. Neighbors. We could also use that variable name. Where is G? So for its neighbor, if the neighbor is not in steps, then we add it. Right? If the neighbor is not in steps, if the neighbor has not been seen yet, Then we add it with steps plus 1. Here we swap the queues, and we return -1 if we haven't hit this condition here. This, of course, could also go inside. We could also say if end in steps, return steps of end. It's another way of doing the same, right? If we have seen this yet, then we return this. Okay, so I think we are done for the day. We ended up using complex numbers. I don't know if this is the best idea or not. Probably this can be simplified. Here we are computing twice the dictionary in the reverse order, but whatever. We can. So here we are find start and end positions and replace with A and Z. That's what we're doing. Read the grid and the save as a dict. Here we generate the graph. So we create the graph. Here we do the BFS. Breadth first, search until we find the end position. Here we could also say start instead of end. Start is a list. Initial positions, start. Okay, so start, end. What else? So this Q1, Q2, we could also maybe rename it. So we could say, next. But I think this is fine. Q1, Q2. That's what I like to use generally. And here for the first part, we start with yes. And for the second part, we start with all the positions that have an A. Okay, lessons learned. Well, we used the BFS algorithm. I was used a long time ago to coding this in C++, so we use the Q1, Q2 queues, you do a swap. It's an iterative algorithm, so it doesn't have you don't need to deal with recursion, so that is good. Then we used complex numbers to represent coordinates in a grid. We used this kind of increments here. We used the ORD function to get the ASCII code of a character. This is a way of checking that the character is in this, it is only one step ahead, so it is only one number larger. Then, well, we decided to generate a graph and we generated a graph instead of from where you can go to where, instead of visiting and doing all the checking in the middle. The other thing we did is we used a dictionary. We translated the grid to a dictionary to simplify the code. I think this may have made the code a little bit slower, so we might want to revisit that if we need a little bit more of performance. And what else? Well, I think this is clear. We use the BFS algorithm, check it in Wikipedia or somewhere else, and then we just reuse the same function both in the first part and in the second part. So I think that's all for today. I hope you enjoy it. See you tomorrow.